One of the problems of the linear regression model is to figure out which variables to include in your linear regression model. The purpose of this lecture is to figure out the consequences if you include explanatory variables in your linear regression model that should not have been included. And such variables are called redundant variables. So the setup for this lecture is we have a random sample and I have specified a linear regression model. It's linear in parameters, but it could very well be non-linear in data. So I could have square variables and so on. And some of the explanatory variables could be dummy variables. All the variables that really should not be in the linear regression model, we call them redundant variables. We know a lot of things about the linear regression model. We have said that under the Gauss-Markov assumptions, the OLS estimators are unbiased and consistent. OLS is efficient. And we have learned how to do inference in the linear regression model. In all those cases, our linear regression model was the correct one, and we had no redundant variables. So the purpose of this lecture is to figure out what can be said about the OLS estimator when our model has redundant variables. So to do that, it's enough to consider a pretty simple example, and the example looks like this. I have a random sample consisting of data on a dependent variable y and two explanatory variables x2 and x3. I have specified a linear regression model explaining y with x2 and x3. Now suppose that the following is true. Suppose that the expected value of y, where y is the dependent variable, I have skipped the subscript I because the relationship is applicable to all observations as well as observations out of the sample. And I condition on x2 and x3, so this is the expected value of the y variable if I know the level of x2 and the level of x3. And what's happening here is that this expected value depends only on x2 and linearly so. So even if I tell you the value of x3, that's not going to affect the expected value of y. To give you an example, y could be the result on a final exam, x2 could be the number of hours that you've spent studying for the exam, and x3 could be, let's say, the number of hours you played video games during the course. The result of the final exam will certainly depend on the number of hours you've studied, but given the number of hours you studied, how you have spent the hours that you did not study probably will have no effect on the final result. Since we did a regression running y on x2 and x3, we actually have implicitly assumed that both x2 and x3 may affect the expected value of y. So this is the assumption made by us. If this is the case, then x3 is a redundant variable. So note that being redundant doesn't really mean that it must be independent of y. If it is independent of y, then yes, it's redundant. But just like the number of hours played computer games is not independent of y, they will probably have a negative correlation. But if you control for the number of hours spent studying, then the information in the number of hours played computer games will probably make no difference. So we need to emphasize that our assumption here is not really incorrect, because our assumption simply allows x3 to affect the expected value of y. But we don't say anything about beta 3. So our assumption actually includes the true expression as a special case when beta 3 is 0. So in that sense, our linear regression model is inefficiently specified because I have added a redundant variable. We should avoid saying that it's incorrectly specified, since the true specification is a special case of our assumption. So to figure out what happens in an example like this, let's look at this simulation study. I have two explanatory variables. I have simulated data for the error term, and here is my dependent variable, and it's determined according to the true expression. That is x3 does not influence the expected value of y conditionally on x2 and x3. We can see that because y is determined as a linear function beta 1 plus beta 2 x2 plus beta 3 x3 plus epsilon, but we have set beta 3 equal to 0. So x3 is indeed a redundant variable in this example. So let's say that we don't know that, we are not certain about this, so we actually include x3 in our linear regression model. And here I've done the estimation. I've estimated b1, b2, and b3. So I've done the regression, regressing y on both x2 and x3. This is my inefficient specification based on my assumed model where I allow x3 to influence the expected value of y. Here is the efficient specification where I've excluded x3 and run a regression of only y on x2, which is the correct way of doing things since beta 3 is indeed 0. Obviously, if I had known that x3 was redundant, we wouldn't have this discussion. I would run this regression without the redundant variable, but typically we don't know it. So the purpose is to figure out the consequences of making this sort of mistake of including x3 into the regression model when it really should not be there. I want to point out one more thing in the simulation study, and that is how I have simulated the error terms. I've simulated them such that the expected value is always 0. That means that both of the explanatory variables are exogenous, they don't affect that. And I've simulated them such that the variance is constant, equal to 0.5 squared. So the error terms are homoscedastic. So I have made the Gauss-Markov assumption in this simulation study. So let's see what we can say about a regression model including redundant variables. And here is the first set of results. So I have a LRM, redundant variables, but the Gauss-Markov assumption still holds. So the expected value of the error term conditionally on all the explanatory variables, the included one as well as the redundant ones, is still equal to 0, and the variance is constant. The most important result is the following. The OLS estimator, based on the inefficient specification, including the redundant variables, will still be unbiased and consistent. This is the good news. At least when you include variables that should not be included in your regression model, you are not going to make your estimators biased and inconsistent. Viewed in terms of this regression model, the one down here without redundant variables, those estimators are, so to say, obviously unbiased because they are based on the correct specification. I've estimated a regression model with y on x, and that's the correct way because y on x2, and that's the correct way because it's only x2 that affects y. So these estimators are definitely unbiased and consistent. But what the result tells us is that these ones are unbiased and efficient as well. So even though I have included x3, which I really shouldn't have, I still get unbiased and consistent estimators. You can see that the estimators of B2 are certainly not the same, and the estimate of B1, they are not the same either. And that makes sense because B1 and B2 down here are just calculated using the Y and the X2 data. These ones, B2 and B1, are calculated using the Y data, the X2 data, and the X3 data. So they will be different. To investigate the unbiasedness, let's focus on B2 first of all. Notice that the beta 2 is equal to 1. So for B2 to be unbiased, it should on average be 1. And let's redo the simulations by F9ing, and we should get a number which on average is 1. And we can see from the simulation that that does make sense. There is certainly no clearly distinguishable bias in B2. The same goes for B1 and for B3 as well. Beta 3 is actually indeed 0, but that is what we get for B3 also on average. If I F9 this, you can see that B3 is not far from 0, and it tends to be on average 0. Of course, that is what we will use to test the assumption that x3 is redundant. x3 being redundant is exactly the same thing as saying that beta 3 is equal to 0, and we know how to test that with the t-test. So if I have this data, I can just simply test if beta 3 is 0, and if I do not reject that, then that indicates that it might be the case that x3 is redundant. So that was the good news. Here comes the bad news, and that's the following. The OLS estimator is generally not efficient, and that's intuitively pretty clear. If I include redundant variables, variables that really should not be included, then I waste a lot of data estimating those parameters that are actually 0, leaving me with less information to estimate the parameters of the variables that are not redundant. So the OLS estimator, based on my regression model with the redundant variables, can be improved upon, and generally the way to improve it is by removing the redundant variables. If you remove them, then we know from the Gauss-Markov theorem that you will have the best linear unbiased estimator. So here's the next set of results. Remember, we have the Gauss-Markov variance formula that allows us to calculate the variance of the OLS estimators. The Gauss-Markov assumption must be satisfied for these variance formulas to be correct. So even with redundant variables, the Gauss-Markov assumption is satisfied, and the variance formula will still be correct even if you have redundant variables. That's for the true variances. The same also goes for the estimated variances. They will still be unbiased and consistent. So in this setting, we have the estimated standard errors on the fifth row, and that means that you can trust these standard errors. They are consistent estimates of the true standard deviations. In this simulation study, I can't show you that because I haven't calculated the true standard deviations. So the problem is not that these are incorrect. The problem is that they are unnecessarily large due to the inefficiency of adding the redundant variable. Now there is actually one exception to this inefficiency, and that is the case when x2, the one that should be included, and x3, the redundant one, are uncorrelated. If that's the case, then we actually will not waste any of the data estimating beta 3. And in that case, the OLS estimator with the redundant variables will actually be efficient. But that's a very, very special case. So to illustrate that, I have here a delta parameter, and that is the covariance between x2 and x3. Right now it's set to 0. So right now the data is simulated in such a way that x2 and x3 are uncorrelated. And in that case, B2 from this one and B2 from this are actually equally efficient. You can kind of see that because we have the same standard errors, and that's exactly what tends to be the case. So if you include redundant variables and they are uncorrelated with all the included explanatory variables, then there is actually no cost at all of including them. However, this rarely happens in econometrics. Typically, we do have a covariance, we do have a relationship between explanatory variables, and we can easily see what happens now. So let's increase this to 0.5. That's the covariance. So now I'm actually making x2 and x3 correlated. And we can immediately see that the standard error of B2 went up. And now it is much higher than the standard error if I exclude a redundant variable. The cost of the redundant variable has increased, and the precision of my estimates will be worse. Still unbiased, but a bad precision. This really shouldn't surprise you. It's just a simple consequence of the multicollinearity problem. The more multicollinearity we have, the less efficient are our estimators. And if you include redundant variables and they're correlated with the ones that are included, then you're simply making the multicollinearity problem worse. If we take it up even further, let's say to 0.9, now you can clearly see a very strong correlation between x2 and x3. And you can also see how horrible the estimator with the redundant variable has become. The standard error is now almost 10 times as large, and the precision is incredibly poor, 0.45. Remember, the correct value is 1. It's really bad. You can see that it generally becomes really poor. Here it's more than twice as big as it should be. So the OLS estimator in this case is not very efficient. So that illustrates this result, that the formulas for the variances are correct, but we get unnecessarily high estimated variances if we include redundant variables. But since the formulas for the variances are correct, all types of inference is also correct if it's based on a model where you have redundant variables. So you don't have to worry about that, at least. But the inference will not be as good as if you remove the redundant variables. So confidence intervals will typically be unnecessarily large. And we also have the power of the hypothesis testing will be unnecessarily small. Inference is correct, so the level of significance will be whatever you set it to be. If you set it to be 5%, then there is a 5% probability of incorrectly rejecting the null. But the power will be smaller, so the probability of rejecting a false hypothesis will be much smaller. And of course, the results on inference, we also need either the normality assumption of the error terms or a reasonably large sample.